The hidden reservoir we didn't see coming. Water inside Earth, but not as pools or veins. Water locked into minerals as hydroxyl, single hydrogen and oxygen atoms stitched into a lattice. To hear it the first time, it sounds wrong. Under the kind of pressure you feel 400 miles down, rock behaves like a sponge you can't see. It doesn't drip, it remembers. That layer is the mantle transition zone, a shell from roughly 410 to 660 kilometers deep. It's where olivine, ordinary upper mantle olivine, reshapes into high-pressure forms with room for water. At the top sits wadsleyite, deeper in ringwoodite. These aren't obscure names to petrologists. They're the reason the phrase Earth's secret ocean won't go away. The first hard proof didn't come from a drill. It came from a diamond. In 2014, a blue-tinted fleck of ringwoodite trapped inside a Brazilian diamond revealed what lab experiments had promised for years. Deep mantle ringwoodite can hold substantial water. Not liquid, not ice. Hydroxyl, locked in the structure, on the order of 1 to 2 weight percent. That tiny inclusion, a time capsule of pressure and chemistry, confirmed that the transition zone isn't dry. It's hydrated in the most literal atomic sense. Wadsleyite, the phase just above, can store a similar fraction under the right conditions. Experiments show ranges around roughly 0.65 to 1.5% by weight, depending on temperature, composition, and oxygen conditions. Those numbers sound small until you scale them to a shell that wraps the planet. Even patchy hydration, nowhere near uniform, could add up to the equivalent of roughly one surface ocean. The phrase several oceans gets thrown around, but the caution is real. Capacity isn't the same as inventory, and inventory isn't the same everywhere. So how do we know where it's wet? Seismology started whispering the story first. Waves traveling through the transition zone slow down in places they shouldn't, and they attenuate, lose energy more than expected. That combination hints at higher temperature, a bit of melt, or fluids changing how rock relaxes as waves pass. Around 410 kilometers, where olivine shifts to wadsleyite, and near 660, where ringwoodite collapses into lower mantle phases that can't hold water. Seismologists see signatures that look like dehydration melting. Small pockets of partial melt created when water is expelled into rocks with lower melting points. It's not a fire hose, it's a thin film that changes everything. Electrical imaging adds a second voice. Magnetotellurics, MT, listens to natural electromagnetic fields and measures how easily the subsurface conducts electricity. Dry mantle is resistive. Add water in defects, add tiny fractions of melt, and conductivity rises. MT maps have begun to outline conductive pathways under arcs and hot regions, consistent with hydrous, partially molten domains tapping the transition zone. None of these methods measure water directly. They triangulate it through physics and are non-unique. Melt, sulfides, graphite, or hydrogen in defects can all raise conductivity. The picture they paint is modeled, not uniform. Reservoirs align with subduction corridors in places where plumes might pull material upward. What kept it hidden is simple. It was never free to see. The water is built into the rock, not filling cracks, not forming reservoirs that reflect seismic waves the way liquid would. Under pressure, minerals change shape and chemistry in ways that create sites for hydroxyl to bond. Think of it like a charge stored in a capacitor. Energy held quietly until the circuit changes and the charge moves. Subduction carries hydrated minerals down. The transition zone stores, upwelling spend. The human moment that flipped the conversation wasn't a dramatic field expedition. It was a lab microscope over a flawed gemstone. A geologist looking at a blue speck in an otherwise colorless diamond recognized ringwoodite, a phase that shouldn't exist at the surface unless it rode an elevator up from depth. Then came the analysis. The structure held hydroxyl. The implication landed hard. We didn't just suspect a hydrated transition zone. We had touched a shard of it. But proof is only a beginning. The questions that matter are about movement. How does water get
delivered in the first place? When do those defects in crystal lattices let go and become melt that can climb? And why do some parts of the transition zone seem saturated while others are starved? The answers don't sit at the surface. They live in the deepwatercycle, a long, slow loop that drags ocean water into the mantle, hides it in mineral sponges, and occasionally releases it in ways that rewrite landscapes and climates. To understand the stakes, you need to follow a drop that never becomes a drop. From rain at the surface to a hydrogen atom locked in ringwoodite and back again in ash and steam. The discovery in a diamond told us what is there. The planet's behavior tells us what it can do. Now we go back to the beginning, not of oceans, but of subduction, pressure, and the kind of chemistry that sets timers we rarely see until they go off. The deep water cycle that runs the planet. Start on a rain-soaked ridge above an ocean trench. That water won't stay water for long. It seeps into oceanic crust, reacts with hot rock, and builds minerals that carry H2O without looking wet. Serpentine in the mantle peridotite, lawsonite and chlorite in the altered crust. Every pore, every crack, every cooling fracture invites the ocean inward, and chemistry does the rest. By the time that slab reaches the trench, it isn't just rock, it's a conveyor of hidden water. Subduction is the belt that pulls it down. As the slab dips, pressure rises, temperatures climb, and those hydrous minerals begin to change. Serpentine, full of hydroxyl, holds on deeper than you'd think, then dehydrates as the slab warms. Lawsonite and chlorite break down at their thresholds too, shedding water in pulses that migrate upward into the overlying mantle wedge. That's the shallow chapter most people know. Water lowers the solidus, mantle melts, arc volcanoes are born. But the story keeps going below the arcs, where not all slab-bound water is released. Some of it keeps riding down past the brittle world into the ductile mantle. Here, the mineral cast changes. Olivine transforms at about 410 kilometers into wadsleyite, a phase that can incorporate hydroxyl into its structure. In that pressure window, the slab's remaining fluids find new homes, not as free liquid, but as defects in the lattice of wadsleyite. Deeper still, between roughly 520 and 660 kilometers, ringwoodite becomes the favored host, and it too can store significant water. The slab is now a courier inside a sponge layer, the transition zone. But this is a one-way ride only until the phases change again. At about 660 kilometers, ringwoodite breaks down into lower mantle minerals that don't accommodate water. Where that boundary is warm enough, or where slabs stall and heat up, hydroxyls are expelled. Suddenly, the surrounding rock has a lower melting point than the water-saturated assemblage that just crossed the line. The outcome isn't a river. It's a film of partial melt dispersed along grain boundaries. Dehydration melting at the base of the transition zone. Meanwhile, at the top of the transition zone, something similar can happen in reverse. Upwelling mantle, plumes or broader return flow, rises and cools, and as pressure drops across the 410, wadsleyite becomes olivine again, losing its capacity to hold water. That released water can again trigger tiny percentages of melt. In both places, a little melt changes a lot. Seismic waves slow down and attenuate more than expected. Electrical conductivity increases. These are the footprints we can detect from the surface. None of this moves on human timescales. The loop is measured in millions of years, but the mechanics are immediate at each boundary. Water moves with reactions. As hydrous minerals enter a field where they're unstable, they decompose and pass their water to whatever phase can carry it. In the transition zone, that's wadsleyite and ringwoodite. Above and below, it's partial melt, migrating a little, pooling where structures allow, then being scavenged into rising magmas or frozen into place as conditions change. So the deep water cycle isn't a tidy conveyor. It's a paced exchange, a series of handoffs. Ocean atmosphere water gets bound into oceanic lithosphere at the ridge, altered on the way to the trench, carried downward in slabs. Near arcs, some dehydrates and drives volcanism. The remainder dives into the transition zone, where it can be stored for geologic ages. Later, mantle upwellings tap those hydrous domains and return volatiles upward, where they eventually become gases at volcanoes, hydrothermal fluids in crust, and at the end of a very long loop, part of the surface reservoirs again. Why does this matter? Because water is a lever on rock. It lowers melting temperatures by hundreds of degrees, so melts can form where dry mantle would stay solid. It weakens minerals, enhancing deformation, so plates can bend and subduct instead of shattering. It changes electrical behavior, letting us see deeper with magnetotellurics. It changes how seismic waves lose energy, letting us hear the presence of fluids and melt as they attenuate. In short, water tunes the engine of plate tectonics. Picture that drop from the opening. Never a drop at depth, always a defect, an agent. Its path threads through phase transitions that act like valves. At 410, the valve opens to storage. At 660, it opens to release. Plumes and slabs control which way the pressure goes. When those valves align with a rising column of hot mantle, the stored charge can discharge,
feeding magmas with extra volatiles, priming eruptions to be more explosive, and steering where volcanoes build their cones and calderas. If water controls where and when rock melts, it controls the difference between quiet and violent. And if it can be stored in the planet's middle layer for ages, the timing of its release isn't a weather forecast, it's geology's long fuse. The sponge layer, Earth's transition zone. Drop into the layer that does the quiet work. The transition zone is a band of mantle, roughly 410 to 660 kilometers down, where minerals switch identities under pressure. It isn't a flat shelf. It's a living boundary with chemistry that reacts to what the planet is doing above and below. In this window, the same basic ingredients, magnesium, silicon, oxygen, rearrange into phases that can hold water in ways the upper and lower mantle can't. At the top of this band, olivine transforms into wadsleyite. That sounds like a textbook name until you hear what it does. It takes hydrogen into its structure as hydroxyl defects. In that state, wadsleyite can store on the order of about 0.65 to 1.5 weight% water depending on temperature, oxygen conditions, and composition. Deeper in, wadsleyite transforms into ringwoodite, which also accepts hydrogen, and in experiments and that diamond inclusion can reach roughly 1 to 2% by weight. Not free water, no pore spaces filling up, just hydrogen and oxygen bound into crystal sites, invisible unless you know where to look. Scale matters. Spread even a fraction of a percent of water across a shell that thick and planet-wide, and you're talking the potential of an ocean's worth of hydrogen, unevenly distributed in stone. But this isn't a uniform sea. It's patchy, more like saturated soils and dry pockets in a mosaic. Some sections of the transition zone sit beneath subduction corridors, where slabs have spent millions of years delivering hydrous minerals downward. Others lie beneath stable cratons or away from slab influence, where the supply is weaker. The sponge image holds, but it's a sponge that's been squeezed and soaked unevenly. We can't drill there. So we infer its state from what waves and fields tell us. Seismic waves run slower in some parts of the transition zone, and they lose energy, attenuate, more strongly than a dry, uniform mantle would. That's a clue pointing toward elevated temperature, a touch of melt, or changes in grain boundary behavior caused by water. At the boundaries, the signals sharpen. Near 410 kilometers, where olivine becomes wadsleyite and the water capacity grows, upwelling material can exsolve water and create tiny films of melt. Near 660, where ringwoodite breaks into lower mantle phases that won't hold hydrogen, warm slabs or stagnant piles can expel stored water and again produce partial melts. Those thin melts aren't lakes, they're films along grains that are enough to change how waves travel. Electrical conductivity adds another line of evidence. Dry, crystalline mantle is stubbornly resistive. Add even a little melt or water in defects and the conductivity jumps. Magnetotelluric imaging, using natural electromagnetic variations, maps these jumps as conductive pathways. Under volcanic arcs and some plume-fed regions, MT surveys sketch ribbons and lenses of higher conductivity that match where seismology hints at fluids and melts. None of these techniques measure water directly. Each has ambiguity. Conductivity can also be elevated by graphite or sulfides. But when attenuation, velocity, and conductivity point to the same places, the case for hydrous, partially molten domains grows stronger. Mechanically, this band behaves like a buffer. It stores water in phases that can hold it, metering that water in and out across geologic time as pressures and temperatures change. It also acts like a valve. Wadsleyite and ringwoodite can accept hydrogen when slabs descend into their stability fields. They release it where upwelling or heating pushes materials across phase boundaries with lower water capacity. That's why the capacitor metaphor resonates. Subduction charges the layer slowly. Tectonic reorganizations and plumes can discharge it quickly, in geologic terms, by feeding volatile-rich melts that rise more easily and erupt more violently. Geographically, the pattern makes sense. Under Western Pacific subduction systems, deep seismicity and slab tomography suggest cold slabs ponding and
Warming around 660 kilometers. That's a setup for stored water being released at depth. Under mid-plate hotspots, seismic images sometimes show low-velocity conduits punching through the transition zone, with hints of a broader, hot base tapping that layer. In continental interiors, beneath old, thick cratons, the transition zone often looks more resistive and seismically faster, drier and cooler. That patchwork means the secret ocean is not a single reservoir. It's a set of connected, reactive storage zones. There's a catch we need to accept. The physics we use to see this layer all have non-uniqueness. Low velocity can mean hotter rock,
grain size effects, or a bit of melt. High conductivity can come from melt, from certain minerals, or from hydrogen in defects. That's why the lab work matters. Mineral physics sets bounds on how much water these phases can hold at given pressures and temperatures. Those bounds keep the inferences honest. If a model implies more water than wadsleyite can store at 140 degrees Celsius, the model is wrong. So what is the transition zone? It's the memory foam of the mantle. It takes the imprint of plates and plumes, their chemistry and heat, and holds on to water until conditions force it to let go. When it does, melt appears where it otherwise wouldn't. Magmas carry more gas than they otherwise could, and the surface feels the difference. In arc chains that light up, in floodbasalts that darken skies, in the slow rhythm of a planet breathing through stone. The fuse we talked about in the last act runs through here. This is the place that keeps time. Volcanoes that drink the deep. Arc volcanoes don't just sit above subduction zones by accident. They tap a plumbing system that starts with seawater on the seafloor and ends as steam in the sky. The surprise is how far that water can travel before it matters. Some is shed shallow, yes, but a meaningful fraction rides the slab down into the transition zone. When upwelling mantle or a rising plume intersects that hydrous storehouse, the result is magma that carries extra volatiles from birth. Watch how it changes the recipe. That's a volcano that drinks deep. Take dry peridotite and heat it. Nothing happens until it reaches a high solidus. Add water and the melting point drops by hundreds of degrees. Now small degrees of melt appear along grain boundaries, and those melts are enriched in water from the first drop. They rise because they're buoyant, and as they rise, pressure falls and more water comes out of the crystal structures into the melt, then into bubbles. That's where behavior shifts from gentle to violent. Gas-rich magmas fragment more readily. They don't ooze, they detonate. You can see the fingerprints in volcanic arcs around the Pacific. The Cascades, the Japanese arcs, the Andes, each chain owes its magma supply to water lowering the solidus in the mantle wedge. But the deep component shows up in how persistent and volatile rich some systems are. If transition zone domains beneath a given arc are well stocked, the melts feeding that arc arrive with more dissolved water. The eruptions tend to be more explosive, the gas plumes taller, the ash columns thicker. Not every eruption needs deep water, but when it's there, it tilts the odds. Hotspots complicate the picture. Many are fed by mantleplumes that rise from depths at or below the transition zone, punching through that sponge layer on their way up. If a plume's base spreads beneath 660 kilometers, it can warm and tap hydrous ringwoodite domains, scavenging water that's been stored for ages. Iceland is a case study in mixing. Plume heat meets a spreading ridge, while geophysical images suggest a conduit that intersects the transition zone. Hawaii, though basaltic and often effusive, carries variable volatile loads that hint at deep source heterogeneity. The message is subtle but steady. Plumes don't ignore the transition zone. They interact with it, even if the degree varies by case. On smaller, faster timescales, the effect shows up in magma ascent. Water dissolved in melt changes viscosity. It can keep magmas mobile at lower temperatures, moving through the crust rather than freezing. It also changes crystallization paths. Hydrous basalts evolve to andesites and dacites more readily, building magma reservoirs that are primed for explosive release. When monitoring networks catch rising gas ratios, swelling ground, and tremor, they're watching volatiles unbinding, water and CO2 leaving solution and inflating the system. The deeper the volatile budget, the longer such systems can cycle between recharge and eruption. We don't measure that deep budget directly, we infer it. Seismic attenuation beneath arcs points to small amounts of melt in the wedge. MT surveys image conductive ribbons that trace possible fluid-rich pathways feeding arc roots. Petrology reads the glass and crystals ejected in eruptions, their water contents, their pressure temperature histories. Every line
Points back to the same quiet truth. Volcanoes are not just heat engines, they are chemical engines, and water is their throttle. This isn't just about bigger eruptions. Water in magmas changes how volcanoes build and collapse. It promotes hydrothermal systems that alter rock into weaker clays, setting the stage for sector collapses and lahars. It creates acid fluids that eat conduit walls, widening pathways and destabilizing domes. A deeply hydrated supply keeps those systems active between eruptions, humming with steam, earthquakes, and subtle ground motion. In the wrong place,
a city on a flank, a reservoir downstream. That background activity is the hazard as much as the blast. There's a sobering long view too. Over tens of millions of years, arcs migrate, plumes wax and wane, slabs stall and steepen. Each reorganization changes which parts of the transition zone are tapped and when. Some intervals deliver steady, moderate, volatile flux. Others line up the valves, a hydrated transition zone, a hot upwelling, a thinning lithosphere. The discharge is not a single event, it's a cluster. Decades to centuries of elevated eruptive activity regionally, or the onset of a flood basalt if conditions are extreme. The timing isn't ours to choose, it's set by plate motions and mantle flow. What about the myth of an ocean bursting from below? That's not how this works. There's no free sea ready to surge. The catastrophe is different and real. Volatile charged magmas that can turn a clear morning into night, shut down air corridors, contaminate water, and load the stratosphere with aerosols. The deep reservoir's danger is indirect. It makes more melt in more places more often, and it hands those magmas the gas that makes them efficient at reaching the surface and disruptive when they do. Stand on a caldera rim and feel that steady exhale, the hot breath carrying a little more water every hour than the last. That's the deep cycle speaking. A volcano that drinks the transition zone doesn't roar all the time. It sips for decades, then gulps in a week. When it does, the plume tells you how far down its straw reaches.
Plates, friction, and the grease. You can't see. Plates don't just collide. They grind, creep, and stall along contacts measured in hundreds of kilometers. What decides whether they lock hard or slip quietly comes down to what's in the tiny spaces between grains. Water, sometimes as true fluid in the crust, often as hydrogen in defects deeper down, changes that friction in ways you can't see from the surface, but you feel when the ground lets go. Follow a subducting slab beneath an arc. Near the trench, the downgoing plate drags pore fluids, sediments, and altered basalts into a zone where pressure compacts, heats, and squeezes water out. That water migrates up and along the plate interface, into the melange of sheared rocks and serpentinite that forms the plate boundary. Serpentinization is chemistry's softener, olivine, plus water makes serpentine, magnetite, and hydrogen, lowering rock strength and adding what amounts to geologic grease. A boundary with more serpentine behaves differently than one that's dry. Farther down dip, temperatures rise and those hydrated minerals decompose. Fluid is released again, but now it's at depths where brittle failure gives way to ductile flow. The middle ground between them, the transition from stick-slip earthquakes to slow, steady creep, is where water shows its hand. In subduction zones like Cascadia in southwest Japan, geodesy and seismic networks record episodic tremor and slip, weeks-long, slow earthquakes that relieve strain without the sharp shocks of a magnitude 7. Their migration patterns trace pressure pulses diffusing along the plate interface. The agent that carries those pulses is fluid. Seismic attenuation helps pick out the wet zones. Beneath the forearc, waves lose energy faster than expected. That elevated attenuation, along with lowered velocities, lines up with regions thought to be overpressured by fluids. It isn't the same as seeing water, but it's a footprint consistent with it. Tiny films along grain boundaries, overpressured pockets at the base of the crust, channels in a ductile shear zone. When those pockets connect, the effective normal stress on the fault drops. With less clamping, sliding can begin at lower shear stress, creep, tremor, or a cascade that runs out as a moderate quake. On continental faults, the chemistry is different, but the physics rhymes. Deep fluids rise along fractures, altering feldspars and pyroxenes into clays like smectite and illite. Those clays are weak. A clay-rich fault gouge can host a seismic creep. A clay-poor one is more likely to lock until it doesn't. Changes in fluid pressure, seasonal recharge, injection, or natural pulses tied to deeper metamorphic reactions modulate frictional strength in real time. The system looks solid, but it breathes. Zoom out and you see a pattern, where plates are hydrated either by seawater at ridges and trenches or by deep source fluids along old suture zones. Deformation is distributed and often quieter. Where they're dry and cold, strain localizes until it snaps. Neither end member is safer. Quiet creep can load the lock patch next door. Locked stretches can go decades without a whisper, then rewrite a coastline in minutes. Water doesn't remove hazard, it shapes it. What about the mantle under the plates, the deeper engine? There, water is mostly in defects, not as free liquid,
but its effect on viscosity is large. A few hundred parts per million of hydrogen in olivine can lower viscosity enough to alter how the asthenosphere flows. Softer mantle zones become channels guiding slab rollback and trench migration. Softer shear zones at the base of plates decouple crust from mantle, letting plates glide with less basal drag. Over millions of years, that changes where stress accumulates above. A hydrated asthenosphere is an invisible conveyor that shifts where mountains grow and basins sag. Electrical methods let us trace some of these pathways. Magnetotelluric transects across arcs and forearcs pick up conductive layers at the base of the crust and along the slab interface. Zones where fluids, melts, or hydrogen in defects boost conductivity above the background resistive mantle. Seismic studies add the attenuation map. Together they outline corridors where fluids likely migrate. They also expose a hard limit. Conductors don't tell you pressure. A wet, low-pressure system can be as conductive as a wet, critically overpressured one. The difference between the two is the difference between steady creep and locked instability. That's why geodesy and microseismicity matter. They add motion to the picture. You can see the human stakes in places like Cascadia. Offshore, a broad, gently dipping interface shows tremor that marches along in 3-week waves every 14 months. Onshore, metropolitan corridors sit on soft sediments that will amplify shaking when the locked part of the interface breaks. In between, a conductive forearc channel suggests fluids are moving now, not just in the past. The deepwatercycle reminds you that the source of those fluids isn't only the shallow dehydration above the arc. It stretches down into the transition zone that feeds the wedge and modulates its strength. This is the grease you can't see. Water that changes the rules without announcing itself. It lowers friction where you'd want it to, until the patch that stayed dry decides to fail. It weakens rocks that would otherwise jam, redirecting stress into neighbors that weren't ready. It doesn't care about zoning or building codes. It follows gradients, reacts at thresholds, and keeps time on a clock longer than cities last. And yet, by listening for tremor, mapping conductivity, and tracking ground motion down to millimeters, we can watch the grease at work. We can't drain it. But we can learn where it pools, how it moves, and when a quiet slip is the sound of a bigger release preparing in silence.